All right, let's go ahead and get going. Before I take questions from you, did people see that I put a new quiz up last night? It's quizzes. I mean, a quiz is just where I put it, but it'll take you maybe 3 minutes to do.
Practice 10.
No, not that it's and the only reason, the reason I put it there is just like I got a little spooked last time about that it wasn't more common knowledge when and where the final was and stuff like that. So it was just me tricking you into making sure you know where that is. There should be 5 free points. 5 multiple choice questions. You can try it. Any questions about anything at all? Go ahead. Just get it going. Everything. So I mean, it is comprehensive. So from section 1.3 up to 5.4, not counting the things that I skipped, but I can't remember. There were a few sections we didn't look at, and I don't remember off the top of my head what they are. But yeah, if you look through like the slides and the videos, and I would pay special attention to the tests, the homeworks, the quizzes, things like that. That should give you a good idea of the things we've done. Again, I have a bunch of quizzes and tests and stuff. I've tried to hand them back, but if you haven't been here and you are missing some things, let me know and I still have them. What else? Did you see my announcement for when like the last office hours between now and the end of the semester are? Okay. So today at 2 o'clock, so my normal Friday stuff. And then you'll have to remind me because it's not typical, but I think I said Monday from 3 to 5, something like that. Okay, yeah, Monday from 3 to 5, then Wednesday from 8 to 9. Those are on Zoom. Yeah, I'm not. So I will not be back on campus until Thursday of next week. So yeah, if you want to meet with me, I'll make time for that, but it'll be on Zoom. You're a fan? Maybe, but maybe not. It's going to be, so that shouldn't be a surprise. She'll be some multiple choice, mostly free response. It's going to be significantly longer because it's the final and you have a lot more time to do it. But in terms of the format, that shouldn't be too out of the ordinary for what you've seen before. What else? Go ahead, you're good. Oh, oh yeah, sure. So, you have a specific example in mind? Okay. So let me try to I'll just give you a function that. Yeah. Yes. Is that the only option I have is those two things? Oh, no, it's not. That better? Okay. All right, so the inverse function theorem, let's say f of x is equal to 1 over the square root of x plus 4. And let's say, for example, I want to find the derivative of the inverse at, what's a good point? Will that work? Is 1 inside this thing's range? Yeah, I think it is. Okay. All right, so how do you want to find the derivative of its inverse somewhere? So how do we go about doing things like that? Sebastian? I mean, you might as well. I mean, you need the derivative of this function, so we might as well do that. So, what is the derivative of this function? Or should we do something before I start jumping into this derivative? All right. Okay. So I think setting it up in terms of power rule is good. All right, so there is my. All right, so now from there, what is this derivative?
X plus 4 over 2.
I don't think it's going to be over 2. So I think if it was just square root of x plus 4, yes. But this is going to look a little different. So negative 1/2 times this thing, x plus 4.
Oh, wait.
Negative 3/2. Yeah, so yeah, our power of the parent function was negative 1/2. So I'm going to have one less.
I was adding.
Oh, yeah, that's integration.
Yep.
All right, so don't have to worry about chain rule here. I mean, you should, just so you don't fall into the trap of forgetting it, but yeah, the derivative of the inside function is just 1. So this thing doesn't look very appetizing, so let's rewrite it a bit. All right, so we have, that's the derivative now, right? So we know that's something we need, so what can we do with it? What?
I remember it, the inverse is not the or 1 over that would be the
Right. So I mean that the theorem itself basically says, you know, if you have some function f that's invertible, then invertible and differentiable, then this derivative is equal to this. It's 1 over the inverse of the derivative at 1. Do I have that wrong? Yeah, absolutely. Yep. So is the derivative of whatever the inverse function is valued at 1. All right, so we got the derivative. Now we really need to figure out, though, is what is f inverse of 1? Now remember, the whole point of using the inverse function theorem is so that we don't have to take the inverse. How'd you get negative 3?
that makes it 1.
Right, so think about the equivalent here. F inverse of 1 means that 1 is the value of the function, and I want to find the x value that delivers that. So this f inverse of 1, that's the same as me looking at this. I want to know what value of x gives me that output of 1 from the original function f. So essentially, from the way you were talking, it sounded like you Yeah, it sounded like you were solving an equation in your head, which is essentially what we're doing. I want to set this equation equal to, so I want to set the function 1 over radical x plus 4 equal to 1. And that gives me radical x plus 4 equals 1. Square both sides, I get x plus 4 equals 1, x equals -3. Sebastian? That is not, so I could invert this function. I am trying to avoid that. I mean, the real purpose of this function, or of this theorem, it is to find derivatives of inverse functions when you can't easily get the inverse. This does not mean, here's the problem with me trying to come up with an example on the fly. Those are hard to come up with. This function is easily invertible. I think the very first example I showed you was something like this. It was like f of x equals x plus cosine x. That can't be inverted. So really, your only hope to deal with to figure out derivatives of the inverse of that kind of function is using this. And I think one thing we should do is invert this, and let's just do this directly and show that we get the same result. So we know that f inverse of 1 is -3. So really what we're finding is 1 over f prime of -3. And how do we find f prime of -3? 2. So I'm setting the derivative equal to -3. Okay, good. So I want -3 to be the x value. This derivative, so -1 over 2 times 1 to the 3 halves. So that's 1 over -1/2 equals -2. Let's verify that using a more direct approach. So if I want to invert this, y equals 1 over radical x plus 4. And I get x squared equals 1 over y plus 4. Y plus 4 equals 1 over x squared. Where y equals 1 over x squared minus 4. So that's f inverse, right? Sorry about cramming everything in. I wasn't. That is the inverse of that. So I found the inverse, so now I can just take a derivative of it. So if f inverse of x is equal to 1 over x squared minus 4, what is f inverse prime? I believe it is -2 over x cubed. You okay with that? From there, what happens if I take that, or if I evaluate that function at 1? Should be -2, right? So kind of use this so we use the theorem, and we just did it directly by inverting it and then differentiating it and still got the same place. Any questions here? All right, what else? Question? From the current one? 545? All right. -6 to radical x. Cosine t over something? Cosine t over t to what power, I'm sorry? 14? That's weird, okay. All right. All right, cool, and I wanna do what? Find dy dx? All right, so looking at fundamental theorem of calculus. All right, how do I deal with this thing?
So you want to
Right. Yeah, so right now, and I'll tell you just basically like maybe 3 weeks into Calc 2, you'll be able to do that. But it just, right now we don't have a weapon, nor do we really need that. So what you're saying is it's basically just, so cosine of radical x over radical x. Yeah, 14. Doesn't really matter. I mean, oh no, it should be outside. I'll keep it faithful, but is it clear why that doesn't matter? It's basically you're multiplying exponents, so it doesn't really matter which order that happens. And then you said also subtract what happens when I do this, right? All right, are we okay with that? Yeah, so I think let's go back to basics. Recall, do you have something? So I think what you're getting at is this. Let's say that f of t is equal to the integrand, so the function I'm integrating. Is that what you're getting at?
Yeah.
So from here, I know that, so there's got to be some antiderivative, right? Which I'm telling you exists. I'm not going to worry about finding it, but it exists. So based on, either this theorem or the fundamental theorem of calculus, is there another way I can rewrite y? Yeah, so really it's going to be capital F of t evaluated at these two limits from -6 to radical x, which is going to be equal to f of radical x minus f of -6. So when I take a derivative of this dy dx, what's going to happen to f of radical x? Well, for right now, let's just keep it in terms of big F little f. I think that'll help me illustrate what I'm trying to get to. But you're wrong. You're right. So, did you mean large F or large F prime? Because remember, I'm taking a derivative now. So large F prime of of square root x, right, times the derivative of square root of x itself, right? So that's a chain rule thing. Yeah, because I am taking the derivative of this function.
this function capital F that I'm representing in the inheritance is not a function F. So the first thing I have to do is take it rid of this.
Yeah, absolutely. So yeah, that's what we're building up.
So technically, that's
Yeah. So before I write that down, are we okay with what's on the board right now? I don't want to gloss over that chain rule a bit because that is one of the two most important things to look at here. But you're absolutely right, is that the relationship between f, lowercase f, and capital F is this, you know, depending on which way you want to look at it, this derivative or antiderivative. So yes, this is in fact f of radical x. And what is the derivative of radical x? 1/2 radical x. Do I know what f of radical x is? Yeah, sure. I know what I know what f is. I named it this. So this is cosine of radical x over. Can we simplify radical x to the 14th? X to the 7th times 1/2 radical x. So this comes out to be cosine radical x over 2 x to the 15/2. Can't think of a less icky way to write that. So do you see the difference? So look at, you know, what we've. This is what you're supposed to do. So I think what I would advise for these is let's first look at what this function is doing. So our independent variable is pretty much always x, right? What am I doing to x? Let's follow x from like beginning to end here. What am I doing to x first? I'm square rooting it, right? And what comes out of that is square root x. And then what am I doing with that radical x? I'm not plugging in the function f of t. I'm doing right. So I'm using it in this this integration process. So let me write this down and I'll talk about what's really happening here. So x falls into this integral. So this integral has a lower limit of -6 and an upper limit of radical x. So the only real place this radical x factors into this integral, well, I shouldn't say only because it makes it sound like it's not important, but it really is. But it is the upper limit of this integral. So let's talk about this. In this integral, as far as this integral is concerned, is t. So let's draw a picture here. -6, radical x. This function does something. I don't really know what it looks like. These are all t values on this axis here. And let's stick with the area formulation of what an integral is. If my lower limit is -6, what values of t am I going to integrate? Because of that, I'm really just treating this radical x, you're treating it like a constant. The radical x just tells you, when am I done integrating? How far to the right am I looking on this area? So yes, x is the variable for this overall function, this integral defined function. But as far as the integral itself is concerned, t is the thing that changes. T is going to take every single value from -6 all the way up to radical x. Any questions on that idea? It's subtle, but it's very important. All right, this little block diagram for this, basically x is the only, what comes out of the other side of this x is something I don't have a ton of room to write down. Actually, this will be capital F of radical x minus capital F of -6. So that's kind of like this two-step schematic process for how x gets run through this function. So if I were to take a derivative of this, starting from the outside, I'm going to take a derivative with respect to x of, the furthest right thing, kind of like the final step in this process. So I'm taking derivative of this integral function with respect to x, but that integral function was not written in terms of x. So the next thing I have to do is multiply that by the derivative of, actually, what's the right way to represent this? Well, think about that. Think about it this way instead. I'm going to take the derivative of the outermost thing with respect to radical x. Kind of a weird way to see that written, but that's really what we're doing when we work the chain rule, from the outside. I'm going to take the derivative of this integral block with respect to whatever its input was. Then I'm going to take the derivative with respect to x of radical x. So I mean, clearly you've all improved a lot at, working with the chain rule, using it for derivatives. Try to ground this thing in the fact that this is substantially the same situation. It's just now you have a much more involved looking function. It's based on this new thing called an integral. Any questions about how we wound up where we did? Cameron?
So super quickly, we kind of dropped the whole cycle of -6 because the derivative of that would
The derivative of that would be 0.
be.
So what's the derivative of any constant? 0. So think about it this way. Yeah, derivative of x is 1. Okay. So, and just to kind of drive that home, remember that a derivative tells you the instant rate of change or something. If something is constant, it has no change. So yeah, and I think Jordan said this last time, or maybe asked this, does it matter what constant this thing is, this lower limit is? Now, for our purposes, no. Because we're going to take a derivative of it. It absolutely changes what the value of the integral is, but that's in the end not really what we're after. We're after the derivative. Any other questions about this? Sure. This is going to be, actually it takes a while for YouTube to process it. What else? Tyler, go ahead.
Yeah.
Okay. This is from a test? Okay. Can you read it again, please? Okay. So car is going 50 miles per hour and 2:10 p.m. Car is going 80. And what am I being asked for? Find the acceleration. Oh, forgive me. That must be achieved. Okay. All right, so how do we go about this? First of all, do we need to remind ourselves what the mean value theorem says? Okay, what's the mean value theorem say? Is that always true or just for certain kinds of things? So F is, I think it's not only continuous, right? Yeah. F is continuous and differentiable.
Or different things, right? Like what's included.
Yeah, so I'll say this over. So continuous on the closed interval and differentiable on the open interval, respectively. All right, so that, and those are the only two conditions, right? For the mean value theorem. I have a function that's continuous over a closed interval, differentiable on an open interval, or the associated open interval. If I meet those two conditions, what do I get to conclude? What must be true? I think we already said this, but there is a C on this interval.
I mean,
Not necessarily zero. Yeah.
also,
So Cameron, there is a theorem called Rolle's theorem,
yeah, that's.
which is a much more limited manifestation of this thing, but yeah. So that's if the endpoints are equal, there has to be a point in the middle where the derivative is zero, but this is, the endpoints can be anything for this one. All right, so here's the theorem. How do we relate it to this context of these cars? Okay, so we know speeds. So let's talk about our variables here. T is the time, right? Right, so what should our, in this context? Sebastian? I guess you want to call time X instead? You sure it's correct? You sure it's incorrect? So are we dealing with distance here? Not directly. I mean, yes, anytime you're dealing with speed, you're looking at a distance, but this is kind of what I'm after here is if we're going to make this theorem work for us, we need to identify what these things are. What What is my function f and what is my function f prime? Do I have things here that where one is the rate of change? Right. So F, I'm going to call that the speed, just spelled with a P. Speed at time X. And F prime, by definition, then, would be acceleration at time X. All right. So I think that is probably the most important way to get started here is to figure out, like, it's hard to apply mean value theorem if you don't know what your underlying function and derivative are. Can we assume that the speed of a car is differentiable and continuous? Yeah, unless you're like teleporting or doing weird stuff, like you have to go to all the points in between A and B. And your speed can't change instantaneously, it has to change gradually. So continuous, differentiable. So now what can I do with this thing? Now that I know I've met the conditions and understand what functions I have to deal with, where can I go from here? Yeah, what are my A and B in this case? I would say this. Let's say A is 0. I think I would go 10 over 60. And you could do 10, but here's the problem. I want it all in the same thing. Hours probably makes the most sense, but yeah, as long as you're consistent, you're going to get there. But I think for this question, I probably asked what the acceleration would be in miles and hours, right? Miles per hour squared. So because that, I'm going to say that A equals 0 hours and B equals a sixth of an hour. So then I'm going to have F of 1/6 minus F of 0 over 1/6. What is F of 1/6? 80 miles per hour minus 50 miles per hour over 1/6 of an hour. So I get 30 divided by 1/6, right? So 180 miles per hour squared. So at some point, that car had to have that acceleration. Could have had it the entire time, could have had it only once, could have had it twice. Don't really know beyond that. I just know that it had to get there once. Any questions about that? Go ahead. 180 value, 180, would that be C? That would be F prime of C. Yeah, so we are not asked to find C here. Yes, but we don't. Yeah, so I couldn't ask you to find C. But what does the mean value theorem tell you? Is that there is a C. There is a time when this car was accelerating at that rate. But yeah, beyond that, we couldn't tell you when it was. If I gave you enough information, you could. And we've given you mean value theorem problems like that, where, all right, here's the value that the mean value theorem says must exist. You have the function, go find the places where it happens. Anything else on this? All right, what else? Oh, for like total distance?
Yeah.
Yeah. Oh, yeah. Let's say I have a thing moving around like this. X of t is equal to 2 cosine of t minus 1. Find the total distance in the first 5 seconds. All right, I want to find total distance. How would I get this started? Sebastian? Integral? So will this right here give me the total distance? That would give me displacement. So that's a key distinction here. So let me draw a rough idea what this graph is. So going from 0 to 5, this is going to go between 1 and -3, I believe. So what's the amplitude of a cosine? 1, right? So I'm going to double that. So basically, if it was just cosine of t, it would just oscillate between -1 and 1, right? The fact that I'm doubling that would make it oscillate between -2 and 2. And then I'm going to shift the whole thing down by -1. I think that's probably the most direct way to do it. I mean, just if you break it down into, transformation of functions type stuff. Are you okay with the fact that cosine oscillates between -1 and 1? Yeah. Oh, yeah. I mean, they were like quadratics, right? So this isn't not gonna act any differently. I just wanted to choose something that was not like something exactly like something you've seen before. But the most important thing here is kind of set up intervals, and this works fine for that. This is going to start at 1. Basically, it's going to act like this, indefinitely. So it's going to be positive at some points, negative at others. Oh, yeah. So I am looking for these areas. I'm going to have an area here, and so on, right? So what's going to happen if you evaluate this integral just as the way you wrote it? You get displacement, right? And by the way I've drawn this graph, what would you expect to come out of that? Something negative, right? Which is not consistent with the way we define distance. So if I want to find total distance, what do I really need to do? I need to do the absolute value. But here's the problem with that, just from a practical standpoint, don't really have a way to do that directly. Right. So yes, I will have to split up this integral, but how do I do that? Find the what? So I need to find these points here. How do I find these points? Right, so I'm going to set this thing 0, And I'm going to ask you to verify this later because I want to give Yana some time to talk to y'all. But the t values I'm going to get from this are going to be pi over 6, no, pi over 3, and 2 pi over 3. So based on those two t values, how would I set up the integral? Actually, let's just do the first couple integrals to find my my total distance. Okay. So I'm telling you at least this is true about this graph. It starts off being positive.
Yeah.
So what am I allowed to integrate there? Yeah, I'm just going to integrate x to t. What would the next integral look like, or next interval be? Right, and I'm also telling you that one's going to be negative. So how do I need to alter this integral to make sure I get the value I really want? I'm just going to do a negative. Think about what absolute value really does with real numbers. It passes positive numbers, basically positive number in, positive number out. If you give it a negative number, it just takes the negative of it. So we can treat these integrals in the same way. So is this integral right here going to be positive or negative? Is this one here going to be positive or negative? Negative, which is why I'm subtracting. Does that make sense? Okay. So I'm not too concerned right now with getting a number. I think what has really hung you up is, based on the few people who have talked about this, is setting up those integrals to make sure you're really getting after the quantities you want. What's 2 pi over 3? Cool. What would the next one be? Of what? What am I integrating? And am I adding or subtracting that one? Why? Okay. We okay with that? All right. Yana, take it away.
Thank you. I was talking about my son. I know I don't actually problem. This is some words to school. Scholarship program also have solutions. So we send you and you can see how your problems are going to be applicable. And then okay, 30 days, Tuesday. Now, I'm sure a lot of people like school a little bit over relation day. So you're actually customizing what's going to be this problem. We send one in the afternoon and one in the evening. And finally, the test program has to be back to the community. Really, you guys are work on I used to have one that is I think the problem that measured around like only this year. Want to understand? far as the water makes you water, so you pass it around. Also, so your this program is 100% anonymous. We'll never know who you are. And yeah, there is something that it's just and for